and welcome to this manufacturing systems technology part 2 module 28. In the last module we were talking about the different distributions, that is the Poisson's distribution, normal distribution, binomial distribution, and how you can relate that to acceptance sampling. This module we are going to actually start plotting some of the control charts based on acceptance sampling plans, particularly the P chart. So, let us first look at what are the kind of control charts which are available for attributes or quality parameters which can be judged without mentioning any appropriate quantity, only qualitative judgments can be passed. So, there are several different types of such control charts that may be deployed. One of them is the P chart. The P chart is basically again the chart for fraction rejected as non-conforming to specifications. You have already found out with a particular p value in a certain situation in a certain binomial distribution, now the mean and average etcetera can be calculated. Then there is the NP chart, and this is the control chart for number of non-conforming items. So, one of them is non-conforming to specifications. So, there may be some specifications, and P chart basically shows whether at least one of the dimensions or one of the quality parameters which are there are away from the specification. So, that makes the part to get rejected, okay. And NP chart is basically in terms of the number of non-conforming items, that is in a lot of let us say 1000, if the P is about 20%. So, 200 of the 1000 are rejected because of non-conformance to specification, and so if you can plot the NP somehow value, that becomes the NP chart. Obviously, there is another C chart which basically is the control chart for non-conformities, and the C is typically the number of occurrences of a certain non-conformity and is being estimated through Poisson's distribution as we have detailed earlier. And then obviously, the U chart, where the control chart corresponds to the number of non-conformities per unit. Okay. So, C chart is sort of an occurrence of a non-conformity, but in a non-conformity you can have many specifications which run out, because of which more than one specification sometimes creates a problem that you have two or more defects within the same non-conforming piece or non-acceptable piece which you are doing in acceptance sampling. So, the U chart is a plot for actually keeping a track of the number of non-conformities per unit vis-a-vis C chart, which actually talks about the number of non-conformances in a production line. So, having said that, let us first think about the control chart for fraction rejected. The most versatile and widely used attributes control chart is obviously the P chart. This is what we are going to stick to at this time. This is the chart for fraction rejected. Obviously, you know what fraction rejected means, and this means that the rejection has happened because of the non-conformance to some specifications. And the principal advantages that these charts provide is that only one chart is sufficient to describe tens, hundreds, thousands of quality characteristics by classifying the item as accepted or rejected. So, even if you have many dimensions which are non-conforming on a single piece, still you can classify the piece to be either accepted or rejected based on whether one or more of the specifications are falling out of range. Okay. So, you are basically trying to increase the sample size by just comparing one characteristic, whether the overall sample is being rejected or the overall sample is being accepted. So, in a P chart, the control limit basically comes out to be, again this is the standard deviation for the P, this is the mean for the P chart, as I think we had illustrated earlier for subgroup size of I. And so, you are basically trying to plot the chart within P plus minus 3 times standard deviation of P, which is P into 1 minus P by Ni, or with a plus minus 3 to it. So, that is how you can plot the control limits. One practical difference between the X chart that you had plotted earlier and P chart is the variability in the subgroup size in the P chart. It can have a list of subgroup sizes which are completely different. We will show this in the example problem later on. P charts typically use data taken for other purposes than the control chart, where subgroups consist of daily or weekly production or tend to vary a lot. Whenever a subgroup size is expected to vary, a decision must be made as to the way in which the control limits are to be shown on the P chart. There are 3 solutions to these problems. One is compute new control limits for every subgroup, show that these fluctuating items limits on the control chart. This is illustrated in the first 2 months of the 4 months. I will show you one problem example where I will actually do this. Okay. So, estimate the average subgroup size for the immediate future, compute one set of limits for this average and draw them on the control chart. Whenever the actual subgroup size is substantially different from this estimated average, separate limits may be computed for the individual subgroups. And the third solution is that draw several set of control limits on the control chart corresponding to different subgroup sizes. A good plan is to use 3 set of limits, one for example, one for expected average, one close to the expected minimum, and one close to the expected maximum. So, I am going to plot and control all these things in a P chart. Let us look at the database here. So, you are doing the computation of trial control limits for control chart for fraction rejected item, and this data is based on a single quality characteristic. So, we are not adding the complexity of many non-conformities in one sample. It is a part of an electrical device, and date wise there has been recording as to how many have been inspected and how many have been rejected. So, you can see that on 6th June about 3350 items were inspected, out of which 31 was rejected. So, the fraction rejected came out to be about 0.93%. Similarly, on June 7th it was 3354, number rejected is about 113, fraction rejected is 3.37%, so on and so forth. So, this shows daily basis what is the number of items inspected, and you can see that the subgroup size here of the inspected numbers are quite variant. Okay. So, that is one good issue about computing this particular control chart, and so the number rejected also accordingly varies. And what is interesting to see is that the percentage rejects also is varying quite a lot, because obviously the fraction rejected when the subgroup size or the sample size is too large would be tending to be the average sample average of the whole distribution. So, the 3 sigma limits are being computed according to the formulation 3 root of p dash 1 minus p dash by root of n, where this p dash is basically the average fraction rejected. So, let us look at the average here, right about here. So, it is basically 880 total number of rejects out of total number of inspections 60,688. So, the average number of fraction rejects in the old distribution is 0.10145. So, about 1.45%. And you can see here that on the, let us say, the 27th day of June, more or less the whatever is the percentage reject is very close to the distribution's overall average number of rejects. So, that is p dash value. So, you put the p dash here, and what you need to do is to sort of keep varying n, because as you know the sample size every time or subgroup size every time is varying in this case. So, you will have this particular entry for calculating this 3 sigma. You only need to vary now the subgroup size, which is actually quite variant, as you see from between all these different days, June 6th all the way to June 30th, the subgroup size is varying. Every time the number of inspections on particular day is quite different than the others. So, the 3 sigma limit has been computed here as 3 times of root p dash times of 1 minus p dash, and that comes out to be in this case 0.3586. So, this value has been obtained by dividing this 3 times of root p dash 1 minus p dash 0.3586 divided by root of 3350. Similarly, this value has been calculated by this 0.3586 number divided by root of 3354, and so on and so forth. So, that is how you calculate the 3 sigma limits. Obviously, UCL and LCL are p plus and minus 3 sigma. So, p plus has already been initiated at 0.0145. So, you are basically changing the values based on whatever is their numbers from case to case by changing a variation or by looking at a variation in the sigma, and you are doing p dash plus 3 sigma and p dash minus 3 sigma for UCL LCL. So, obviously, this is a data out of a larger much larger data. Actually, it is actually a 4 months record of daily 100% inspection of a single critical quality characteristic, which is a part of an electrical device, and we will show you the later on data for the next 3 months all the way up to September. Only thing is, in this case we will need to understand that after the first month how you can vary the control limit, so that you can keep plotting the p chart in accordance. When after a change in design, the production of this new part was started early in June, the daily fraction rejected was computed and plotted on a chart, and at the end of the month the average fraction rejected p dash was computed every time. So, at the end of June, for example, the average fraction rejected is about 1.45%. Okay. So, now the trial control limits have to be plotted for each point. A standard value of fraction rejected p0 was then established to apply to the future production, and during July new control limits were computed and plotted daily on the basis of the number of parts and inspected during the day. So, let us look at how this control limit is established. So, here for example, if you look at the 3 sigma control limits on a p chart, depends on the subgroup size. So, this is the control chart plot for the P chart for the first month. Let us say we are talking about June 30th up to June 30th, and as you can see here we are plotting the varying UCL and LCL based on P dash plus 3 sigma and P dash minus 3 sigma, and these are typically the assembly of points which have been computed here. Let us go back to the table. So, you have a UCL and LCL, and you have actually different values of the UCL and LCL on a daily basis, which you are actually plotting as the upper control limit and the lower control limit through this broken line. Okay. So, this is broken line. Obviously, the average value of the fraction rejects is about 1.45% in this particular case. So, as has come out from the P dash value, if you remember, as calculated in the table. So, that is how you can plot the upper and lower control limits. Once the limits are defined now in the P chart, we now start looking at the individual points and see what are the outliers. And here in this particular case, I can say that there are many points. So, these are the individual points. For example, this is corresponding to the case 7th of June, where there is an outlier 0.037, and it goes above the upper control limit. Similarly, there may be many such cases which are there from time to time. For example, this again is an outlier. June 12th is an outlier, because 0.0209 is actually greater than the upper control limit in this particular case. Okay. And so, similarly, there may be cases where it goes below the lower control limit. So, in a nutshell, if you look at the days June 7, 12, 13 and 22 are basically the outliers. If I just look back in the data calculated in the June point. So, 7, 12, 13 and 22 are the outliers, as you can see here. So, in case of 7th again the upper control limit is exceeded, in case of 12th again the upper control limit is exceeded, in case of 13th the upper control limit is exceeded to a large extent, case of 22nd again the upper control limit is exceeded to a large extent. The remaining values are all within the control limits, and so you can safely take them. So, what you have to do now is to take a decision for the next month to determine the UCL. So, you basically remove these values which are outliers, that is June 7th, June 12th, June 13th and June 22nd from the overall calculation. That means, from the overall P average value that you have computed. So, you take out 70 items, 339 items, 68 items and 31 items from the number of rejected, and similarly you also take them out from the number inspected, like 3350, 3354 item on 7th, 3252 item on 12th, 4641 items inspected on 13th. So, you are basically completely eliminating these 4 points which are outliers and finding out the fresh P dash value corresponding to that, and that comes out to be 0.0065. So, because of elimination of these outliers, in the second month when you will try plotting the control limits, you have to take an average value P0, which is formulated by eliminating the outliers from the month of June. So, once that is done now, you can calculate the new limits based on this P0 value, again considering the subgroup size which is there on local basis, and then for the month of July subsequently based on this new value 0.0065, you can see that the control chart now has about 65%. So, the average changes from 1.45% to 65% because of elimination of these outlying points, and so does the UCL and LCL. So, the LCL and UCL in this case are quite lower because you have eliminated the major contributions which are outliers in the first month. So, that the second month is more smoothly plotted. It goes between 2 to 7 all the way to 30 to 31, and you can see here that now you have a again method of plotting the outliers. So, once the limits are determined, you are plotting the individual points corresponding to 2nd of July, 3rd of July, 4th of July, so on and so forth. And let us look at this particular table to find out if there are any outliers. So, you can see again that the UCL here is defined as P0 plus 3 sigma, P0 minus 3 sigma, and we compare the daily fraction reject with respect to the LCL UCL. So, we find out that there are some points, like for example, this case of July 17th, when the fraction rejected is 2.94% and which is completely an outlier again in this particular case. Okay. Or for example, July 24th, when again it is 1.24% and again an outlier because the upper control limit is 0.0112. And so, after plotting this, we try to find out what these outliers are. These outliers are represented here. Okay. So, this probably corresponds to the first outlier. There is another one which actually goes below the lower control limit. So, these outliers again need to be eliminated in a sequential manner, and then the fresh limits are computed, the fresh UCL and LCL values are computed by eliminating these outliers, so that this can be the new governing LCL UCL for the month of August. So, let us look at it how this data is calculated now. So, we calculate a fresh P0 value. So, once you have found out that the number of outliers are lower from June to July, as you can again see back in this curve. So, in June the outliers are much more in comparison to July. So, you have sort of standardized the way that we are having a control on fraction rejects. So, from this onwards, where there are maybe very less outliers or the magnitude of outlying is also very low, you can actually assume now the sample size or the group size or subgroup size, whatever we have considered to be varying so far, to be the average daily production. Okay. And so, therefore, it will lead to the straightening of the upper and lower control limits if we assume the average daily production as now the basis for calculating the UCL and LCL. Let us look at it again on this table 3 right here. So, here the estimated daily average production is basically out of this 31 days, the total production is 73,523. So, it is about 2600 per day, and based on that we are now calculating fixed UCL and LCL values by looking at the fraction reject. Again, this fraction reject would be computed based on what you are eliminating. So, basically here in the first module you had eliminated June 7th, 12th, 13th and 22nd. In the second module, as I told you, you had eliminated July 17th and 24th and maybe also July 7th, which is an outlier again on the lower side, as you can see. And by eliminating these 3, we have calculated fresh P0 value, which comes out to be here as 0.0065. But now obviously, because you want to straighten out the UCL and LCL, we are using, instead of these varying subgroup sizes on a daily basis, the average production, which is 2600 on a daily basis, and that helps you to calculate the fixed set of UCL and LCL in this particular case, which is 0.0112 and 0.0018. So, this is a very critical decision making aspect for the management, that when you want to straighten out your control limits, and obviously you have to look at what is the outlying capacity, or what is, let us say, what are the number of outliers, or to extent which the outlying capacity is there. If it gets minimized because of 1 or 2 iterations, that should be time enough for the management to decide that we now need to have straightened control limits, and then you can calculate everything on the basis of the average daily production. Similarly, in the case of September, you can see again the same trend continues. Obviously, there were some outliers in the case of August, which needs to be further eliminated. So, there was one outlier particularly here, there was another outlier region which is below the LCL, again below the LCL. So, these now values need to be taken off from the August. Let us look at a table corresponding to which outliers these are. So, one of them, for example, is the August 27th, where the total production has gone above the UCL or the total fraction defects have gone above the UCL being 0.0112 and this has gone to 0.0116. And similarly, there are cases where, for example, during, let us say, August 21st, then again the outlier, although the extent is very low, but it has gone below the lower control limit, which is 0.0018, this is 0.0017, and then there is again another August 16th, the same thing has happened here, it has gone to 0.08%, whereas the LCL was 0.18%. So, there are 3 such outliers. You remove these outliers, calculate the new value of P0, which is 0.0051. Again, the average daily production is 2700 calculated, because once you have reasoned or you have made the UCL LCL straightened, there is no way to revert it back, and then the next straightened limits could be calculated by based on P0 new P0 value by eliminating from the last month, and then calculating 3 sigma based on the average daily production. So, here the n value that you are taking is equal to the average demand, just as you took the n value as the average demand subgroup size to be 2600, the average demand on the month of August and September. So, you have taken that critical decision making to straighten the limits from August onwards based on the previous 2 months experience, June and July, because you see that the control limits are within the points are the fraction rejects are within the control limit, and then the extent of the outliers also have reduced. Obviously, the number of outliers have reduced quite a bit. So, it is good time to call on straight limits, and so this way you can plot for the remaining 2 months, that is August and September, as you can see here. And in the month of September, in fact, the number of outliers have almost eliminated. There is only one particular value which is outlying, and this can continue from month to month. Okay, so this is how you basically try to control your quality based on the various aspects of the P control chart here, because it is attribute related. You need not quantify, you can just consider a piece to be rejected or accepted, and it gives you a lot more flexibility than the X chart or R chart, where you can only mention one characteristic dimension based on which you plot the X and R chart. So, this is the Shewhart's acceptance sampling based attribute control chart, and although the correct position of the 3 sigma control limits on a P chart depends on subgroup size, the calculation of new limits for each new subgroup consumes some time and effort. That is a problem, at least for the first 2 months when you are having a unstraightened UCL and LCL. You will have to compute on the various subgroup sizes on a daily basis. Although if the variation of the subgroup is not more than 25%, it may be good enough for practical purposes to establish a single set of control limits based on expected average subgroup size. And that decision can be taken based on the looking at the outliers also and the extent of outliers also. And once the straightened limits are established, then there is no reverting back, and by and large the acceptance sampling plan should be based on operating the values within plus and minus 25% of the actual average daily production, which would be taken in this particular case. So, this in a nutshell is what a P chart is, or how it is plotted. So, you have already learnt about the various statistical distributions, you have learnt about how to plot the Shewhart's control charts with X and R, that is the dimensions or for specific dimensions or quantitative control charts. You have also learnt about attribute control charts. So, we will try to round off the statistical quality control area here, and we will start with a new topic in the next module, which would be more related to the robotics and automation in factories of the future. Thank you.